Welcome. In this video, we'll take a look at another implicit derivative. This one's going to be involving some exponentials and logs. So we'll start like any other implicit derivative. We'll want to take the derivative with respect to x of the left and the derivative with respect to x of the right. So let's go term by term from left to right here. We'll start with this exponential e raised to the x times y. So when I take the derivative of an exponential, I know I always want to take the exponential and rewrite it, and then take the derivative of the exponent. And so there's no difference here. I want to rewrite my exponential, that happens to be e raised to the xy. And now I'm going to take the derivative of my exponent, which happens to be xy. So let's consider the derivative of x times y. This would take the product rule. So I'm going to take the derivative of the first. That would be 1. And again, the first function here I'm going to call the first function is x, and then the second function I'll call the y. So the derivative of the first is just x is going to be 1. Multiply by my second function, that's y. Plus, I'll leave the first, that's x, and then the derivative of y with respect to x is dy dx. So the derivative of xy, if we take it implicitly, will just be 1y plus x dy dx. The next term that we'll take a look at, we'll have the 2x to the third. We'll want to add this, so we have 2. If I bring down the 3, that'll be 6x raised to the second power. And then on the right side of our equation, we have the derivative of 4 times the natural log of y. So when I consider the derivative there, we'll have 4 as the constant, that stays. When I take a derivative of the natural log, we know that's 1 divided by the variable. So that would be just 1 over y to start. But again, we need to take a chain rule since we are taking a derivative with respect to x when we have a y function. So the derivative of y with respect to x, we would say here we have to attach a dy dx term. And looking at this, that would be our derivative on both sides with respect to x. So let's take a look at what we have left and try to simplify a little bit before we go out and solve for that dy dx. So the first thing I can do is distribute here my exponential. So I'll have y e to the xy. That's going to have no derivative terms in it. Next, I'll have plus x e to the xy dy dx. So that's our first derivative term. Plus 6x squared. And then finally, we'll have equals 4 over y dy dx. So we have 2 non-derivative terms and 2 derivative terms I'll work with. This equation looks like it's just easier to manipulate if we subtract this x e to the xy dy dx over to the right side. So we'll subtract there on both sides. When we cancel those out, we'll be left with non-derivative terms on the left. So this would be y e to the xy plus 6x squared is equal to, we can rewrite this side and actually factor out a dy dx. So this would be dy dx multiplied by 4 over y minus xe to the xy. And then the last thing we could do here, just to solve for our dy dx here, is to divide both sides by the function to the right. So if I rewrite this for dy dx, we can rewrite this. This will be our numerator right here, and we'll divide by this term on the right. So we'll have y e to the xy plus 6x squared divide by my 4 over y minus x e to the xy. And this will be our final derivative with respect to x. So we've taken our derivative implicitly here using our exponential and our log terms. A couple rules that we used here was the exponential e rule and also a product rule. Up there in the exponent, and as well we worked with the natural log function. And with the natural log, remember that our general derivative is 1 over the variable, but we had to use the chain rule because it's a variable of y. So hope this is helpful with implicit derivatives. You can check out the next video if you'd like to see some more examples.